Hello, in this video we're going to work out the equations of rotational kinematics. And big spoiler, they are the same as the equations of linear kinematics, just with the variables all switched. Now we can't just say, well, velocity is like velocity, acceleration is like acceleration, therefore the equations are the same. It doesn't quite work that way, so we will actually run through the derivation, but we can do it a bit quicker than we did it the first time. Now, first question is, well, what do we do about these things being vectors? And if we think about it, that's not really much of an issue. So we have some object, three-dimensional object, and it's rotating about some rotation axis. What that means is that the angular velocity can point one of two directions. It can point up or down, but it points along the rotation axis. And likewise, the angular acceleration could point up or down, but it's going to point along that rotation axis. In other words, we really only have one dimension. This is pretty much just going to be 1D. So I don't actually need to write down components to my vectors. Technically I do, but they're all in the same direction. So I'm going to leave off all the vector signs. Our relationship between angular acceleration and angular velocity will give us a kinematics equation. The way we would solve this equation is we would isolate d omega and say that d omega is equal to alpha dt, and we can solve that by integrating both sides. So we have the integral of d omega is equal to the integral of alpha dt. We're going to choose to limit ourselves to the cases where alpha is constant, which will give us a nice closed form for our solutions, just like we did with linear kinematics, where we had constant linear acceleration. Here we also would like to have constant angular acceleration. Now we're not complete at this step yet. We could either have an unknown constant or we could put limits onto our integrals. I would rather do it with the limits. So we have time going from time equals 0 to time t, and then consistent with that we need to have the initial angular velocity. That's the angular velocity at time 0. And then the angular velocity at time t, which we'll just call omega. So with limits, we don't have to worry about an unknown constant. We can just directly evaluate this. The left-hand side becomes omega minus omega naught. The right-hand side becomes alpha t minus 0. And that tells us that the angular velocity at time t is equal to the initial value of the angular velocity plus alpha times t. Let's call that equation 1. But we need more than that. There are more than that. We haven't said anything about theta, about our angular position. Well, let's do that right now. Omega is equal to d theta dt. Therefore, d theta is equal to omega dt. And we can integrate that. We'll go from theta naught to theta, integrating d theta. And that's equal to the integral from 0 to t omega dt. And we know what the form of omega is. The form of omega is over here. That's equation 1. So that's omega naught plus alpha t. And let me clean this up. I'm getting a little sloppy with my handwriting. That's a lowercase t. This is an alpha t dt. Okay, and on the left-hand side, we get theta minus theta naught. On the right-hand side, we get omega naught times t plus 1/2 alpha t squared minus 0 from the lower limit. And so this is an equation. We'll call that equation 2. And we could write this difference here, theta minus theta naught, we could write that as delta theta if we wanted to. And then we can combine equation 1 and equation 2 in several different ways, and that will end up giving us a couple useful combinations. It'll tell us that omega squared is equal to omega initial squared plus 2 alpha delta theta, with delta theta defined as theta minus theta naught. It will tell us that delta theta is equal to 1/2 omega plus omega initial times t, and it will tell us that delta theta is equal to omega t minus 1/2 alpha t squared. So those are the other combinations we can get, chosen because each combination leaves out one of the 5 variables. Does this look familiar? I hope so, because this looks just like the equations of linear kinematics. The difference is we have different variables. In fact, that relationship is kind of nice, that theta is a lot like x, and anywhere we had an x or a delta x before, now we have a theta instead of position, angular position. Omega is a lot like velocity, and angular acceleration alpha is a lot like linear acceleration a. That's not to say that they are the same. They are not the same, but they play similar mathematical roles. That's why they show up in the same place in equations that look the same. And so in fact, many of the tricks you already know for solving linear kinematics works just fine once you've plugged in the appropriate rotational variables instead of linear variables. Okay, that will do it for this section. Moving on, we'll talk about the equivalent of mass for rotational objects, which is called moment of inertia. So I'll see you in the next section.